Okay, as promised, here's the next page of the worksheet. So we're going to work through these together, and then you're going to be on your own for the last couple of questions. So the first one, we looked at compounds of copper and oxygen. Sorry, not copper, carbon and oxygen. In this one, we're looking at copper and oxygen. So it's the same process. We've got two compounds, A and B. And again, they were kind enough to give you things that add up to 100, so you can kind of think of these in terms of the percentages as well. So we see that they're different compounds. So the first thing I want to do is determine the value of the ratio of copper over oxygen. Again, always do it this way, whatever they tell you. So copper to oxygen. So for compound A, 79.9 grams of copper to 20.1 grams of oxygen. And again, don't just leave a fraction like that. We need to calculate this and figure out what I'm really working with. 79.9 divided by 20.1 is 3.98. So that's my ratio for A. For B, I've got 88.8 grams of copper compared to 11.2 grams of oxygen. So that's a ratio of 7.93. Part B, how does the mass ratio for compound B compare to that in compound A? And so again, that may not be quite as obvious as the first one. So we can divide 7.93 divided by 3.98. I'm just doing the big one over the small one. And I get 1.99. So essentially, again, it's a 1 to 2 ratio. So 1 to 2 ratio of A to B. In other words, B has twice as much copper because that's what's on top as A. So remember, the top represents the copper, the bottom represents the oxygen, Cu over O. Now this one's a little trickier. It says express these ratios as improper fractions, and they're not really close to being a fraction that I recognize from that decimal. So like I'd look for like 0.25 if it's a fourth, 0.75 if it's 3/4, and we saw the 0.33 and 0.66 in the last one. But these are just close to whole numbers, and so I'm going to call this for A 4 to 1, and for B 8 to 1. So let's look at our two possibilities here. So in our first hypothesis, just like the last one we looked at, one idea is that oxygen and copper are exactly the same size. So that's my oxygen. We'll use a different color. How about that? We'll use pink. Since we use the other one for carbon. Cu is the symbol for copper. So in A, if I have a 4 to 1 ratio of copper to oxygen, that means I would have 1 oxygen and 4 coppers. Again, that's if they all have the same mass. That's how I would get a 4 to 1 ratio. So this formula would be Cu4O. Now, the way I would get an 8 to 1 ratio of copper to oxygen is 8 coppers for every 1 oxygen. So my goodness, oxygen's there in the middle. And I don't know if I can get 8 of them around there. 1, 2, 3, 4, 5, 6, 7, 8. They don't look, they're quite the same size, but hopefully you get the idea. So this is Cu8O. Looks like a flower. Now the other possibility here is that copper atoms are heavier than oxygen atoms by a 4 to 1 ratio. So that means copper is a lot bigger than oxygen. So in that case, the 4 to 1 ratio would just be carbon has a mass that's 4 times oxygen. And so this is CuO. To get an 8-to-1 ratio, it takes 2 things with the mass of 4 and 1 thing with a mass of 1. So that's 4 plus 4, which is 8, and 1 oxygen there in the middle. So this is Cu2O. And then the question is, which hypothesis seems more reasonable to you? And justify your answer. So again, you know from hopefully biology and other science classes or just the real world that, you know, we really do have these compounds, carbon monoxide and carbon dioxide, in a 1-to-1 and a 1-to-2 ratio. And we also looked at the periodic table and saw that, yes, indeed, oxygen and carbon have a 3-to-4 ratio. Sorry, 2-to-3 ratio. No, I was right the first time. 4-to-3 ratio based on their masses. I'll be all right. If I look at carbon and oxygen, I can't get it right tonight. Copper and oxygen for this one. Copper's mass is about 64, 63.5. Oxygen's mass again is 16. So, oops, 64 divided by 16 is that 4-to-1. 4-to-1 ratio. So for us, I mean, because we know the masses, we know that this is the more reasonable conclusion for these. So we're going to stick with hypothesis 2. Hypothesis 1 just doesn't make sense. If you look at other elements, you know, you would find out that you can't get whole number ratios from other elements, and so some of them just don't make sense at all. So we know that the atoms have different masses. Now, your job is to use the hypothesis we have chosen. Sorry, this is hypothesis number 2. Don't go back to hypothesis 1. We're done with that. I just wanted you to see sort of how the first scientists had to figure things out. And so you're going to do the same things that we just did. So follow the examples here to do copper and chlorine. See how that turns out. Now again, notice chlorine's on top, copper's on the bottom. Pay attention to that. And then iron and chlorine. So remember the law of multiple proportions. We're looking for small whole number ratios. And so it says to be careful there. That's why I'm telling you that. Small whole number ratios. So see how you do with this. And guys, this is tough. This is not the easiest thing to do. And so we definitely can go back and spend some time working on this if we need to in one of our Zooms. So again, you guys work on that. And you've got a few practice problems to do beyond those. And you'll see what I'm talking about there on Canvas. And like I said, we will work some more on this together as you need to. And I expect that we will need to spend some more time. So don't get too discouraged with this. Just do the best you can. And I will be talking to you soon.